Now it's time for us to look at chain rule in multivariables. The idea with the chain rule is when you have functions that are in terms of other functions, how do you kind of pull them apart and get the derivatives that you need? So we're going to start off with an easier one. Suppose that z is a function of x and y, and both x and y are functions of t, and everybody's differentiable everywhere. So then if I want the derivative of z with respect to t, then I would take the partial of f with respect to x and multiply it by the partial of x with respect to t. That gives me the partial of f with respect to t aspect in there, but in terms of x. I do the same thing with the y's. I have the partial of f with respect to y times dy dt. Let's look at an example. Suppose I have z is equal to xy squared plus 5x cubed y, where x is cosine of 2t and y is sine of t. I want to find dz dt when t is equal to 0. First, I need to find the different parts of my derivative. I know that dz dx is y squared plus 15x squared y. I can find that dz dy is 2xy plus 5x cubed. Finding the derivatives of x and y with respect to t, dx dt is negative 2 sine of 2t, and dy dt is cosine of t. Now, grabbing my formula from the previous page, I can fill in the expression. And I put the partial of z, partial of x over here, and the derivative of x with respect to t there, and I plug in all the things that need to be plugged in. Can I simplify this a little bit? Yes. Now, I want to find the dz dt when t equals 0. So let's do some evaluating. I have t equals 0, so that means x equals 1 and y equals 0. So writing this derivative out again, I know that sine of 0 is 0, so all that's gone. I know that cosine of 0 is 1. The 2xy has a y in it, which is 0, so the only thing that survives is 5x cubed. Plugging my 1 in, I get a 5. Now what if I have two variables? So x and y are both functions of s and t, two other variables. We can do that too. Suppose z is a function of x and y, and it's differentiable, and x and y are both functions of s and t, and everybody's differentiable everywhere. So then we want to be able to find the partial of z with respect to s and the partial of z with respect to t. Now, like before, when I do the partials, I want to take the x's into account and the y's into account. But for the partial of z with respect to s, I'm dealing with the s's, and the partial of z with respect to t, I'm dealing with the t's. So let's look at an example of this. Suppose z is equal to e to the x sine y, x is equal to st squared, and y is equal to s squared t. I want to find the partial of z with respect to s. So there's my equation, and these are four things I need to find for this equation. So going through the list, I have the partial of z with respect to x. That's e to the x sine y. The partial of x with respect to s. Looking up here, x is equal to st squared, so that is t squared. The partial of z with respect to y is e to the x cosine y, and the partial of y with respect to s is 2st. So let's plug that into my formula, and let's simplify. Not a whole lot of simplifying, mainly just move some of this stuff into the front. Let's try the other one. Let's try with respect to t. So there's my equation. Now, I need these four things. I've already got partial of z with respect to x and y. So now I just need the partial of x with respect to t and the partial of y with respect to t. Partial of x with respect to t is 2st, and the other partial is s squared. I'm going to fill that into my equation, and again, can't simplify a whole lot except pulling some of these extra variables in the front so they don't get sucked into your trig functions. Well, we've done u as a function of two things, and each of those two things is a function of two things. We need to make this generalized, because that's what we do in math. We take something and make it worse and worse and worse and worse. So here it is. U is a differential function of n different variables, and each of those n variables is a function of m other variables. Then u will be a function of those m variables, and this would be how we would write the partial of u with respect to one of those ti's. Hopefully you can see this pattern though here, because we've got x1, x2, x3, yada 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 down to xn, just like before we had the x's and the y's. And then the ti represents my s's and t's, so we have each of those with respect to the ti. Let's look at a tree, which will make this a little bit easier to wrap your head around. Let's suppose we have this. So this is one where u is a function of 3 variables, and each of the 3 variables is a function of 3 more variables. So if I want to figure out the partial of u with respect to s, well, let's take the path from u down to s. We've got one path there. That's going to give me partial of u with respect to x times the partial of x with respect to s. Now I'm going to take the path in the middle. So that gives me the partial of u with respect to y and the partial of y with respect to s. And then the last path is this one, giving me the partial of u with respect to z times the partial of z with respect to s. Let's do an example. Suppose we have u is equal to x to the 4th y plus y squared z cubed, and x is equal to rs e to the t, y is equal to rs squared e to the negative t, and z is equal to r squared s sine t. I want to find the partial of u with respect to s when r equals 2, s equals 1, and t equals 0. So let's take this step at a time. Don't get overwhelmed by all the numbers and letters and alphabet soup in your head. I know that the partial of u with respect to s has to equal the partial of u with respect to x, the partial of u with respect to y, and the partial of u with respect to z. We have to take each of those 3 variables into account. Since we're doing this with respect to s, multiply each of those partials by partial of x with respect to s, partial of y with respect to s, partial of z with respect to s. Let's figure out what we can figure out. First, I need to figure out what my variables are equal to. If r is equal to 2, s is equal to 1, and t is equal to 0, I know that x will be equal to 2, y will be equal to 2, and z will be equal to 0. Okay, so now we've got x, y, and z. Let's look at my partials. The partial of u with respect to x is 4x cubed y. Plugging in my numbers, I get 32. Partial of u with respect to y is x to the 4th plus 2yz cubed. Plugging in my numbers, I get 16. The partial of u with respect to z is 3y squared z squared. Plugging in my numbers, I get a 0. Ooh, I like zeros. Things fall away when you have zeros. So now I've got those partials. Now I need the partials with respect to s. So the partial of x with respect to s is re to the t, which is 2. The partial of y with respect to s is 2rs e to the negative t. That's a 4. And the partial of z with respect to s, that's going to be 0 again. Sweet. Okay, now let's bring all this crap together. I don't need the x, y, and z anymore, so let's get rid of them. I need the partial of u with respect to x. That's 32. Next, I need the partial of x with respect to s. That's over there. That's also 2. Next, I'm going to need the partial of u with respect to y. That's 16. And the partial of y with respect to s. That's 4. Next, I need to deal with my z's. So I have the partial of u with respect to z is 0. And the partial of z with respect to s is also 0. Let's put all this stuff, plug all this stuff into the equation. Partial of u with respect to s. I have 32 times 2, I have 16 times 4, and I have 0 times 0, giving me a final solution of 128. You need to be organized. If you're messy, you need to work on it. Write things neatly and carefully and take it one step at a time. Figure out what you need and figure out how to get it. Don't try to just come up with the answer all at once. And practice, practice, practice.